Okay, let's start. Okay, so in this lecture, I'm talking about modulated free energy method introduced by Didier Brech, Pierre-Emmanuel, and myself last year to study the mean field limit problems for very singular kernels. Some of them can be attractive, like in the Peter-Keller-Seeger system. So where the kernel is given by the gradient, the negative gradient of some attractive logarithmic potentials. Um, so this part mostly focus on the derivation of a Peter-Keller-Seeger system. So we have a short notes which give the sketch of the more general theories which appeared on the Laurent seminar in France. So yeah, but since we only have like one lecture remaining, we just focus the Peter-Keller-Seeger case. So so we call this modulated free energy method. Basically, is a combination of the relative entropy method. I think we introduced. I introduced with Pierre-Emmanuel Jaban. And the modulated energy method introduced by Sarfati and Durings to study the stochastic systems. But later we can adapt our approach to study vanishing viscosity case as well. Okay, so you will see the formula like in next page, but the idea is the following. So in our previous work, so in my paper with Pierre-Emmanuel Jaban, so if we want to treat very singular kernels like Poisson kernel, like in 2D, if you take the divergence, you get a Dirac mass. So the diagonal, so there's the double summation in the terms I showed you. Like, so maybe I just write a little bit. So there's a problem there. So in our previous work, there's the terms we need to control is like the following. So we take the derivative, formal derivative of the relative entropy between the particle system and the limit. So now, if we just throw away some nice terms, which maybe have the sign, or you can control easily. So there's this type terms. So it's phi xi xg d rho n. So this is, let's say we integrate on some space Rdn. Okay, rho n is the joint distribution. We need to control this type of terms. And if you still remember, so this phi looks like the following. So it's log rho bar x. So maybe up to a sign. So up to a sign. So maybe positive or minus. So but that it doesn't matter. Okay. So here is divergence k x minus y minus divergence k cross rho y. So like these terms. As I said, right, if we treat the Navier-Stokes or Euler equations, the divergence vanish, right? You don't need to really consider divergence term. But if it's really Poisson kernel, the divergence k is Dirac, right? It's very difficult to treat the diagonal term, right? In the summation, there are terms I equals to g. It makes a difference, right, to enter the diagonal or remove the diagonal. So we must treat this very carefully. So otherwise, you might be wrong. So it's actually a very delicate question, like how to add the diagonal, like the self-interaction, and remove remove them first, then like add back, or vice versa. So it really delicate questions, which doesn't, which is not there if we just consider divergence-free kernel or divergence-bounded kernels. But it really becomes a serious problem when we consider like more singular kernels, like in the person case. Okay, so like to cancel these terms, like these band terms, we introduce weights. Right? We introduce weights in the relative entropy. You will see that later. So basically, we usually introduce weights, a weighted version of relative entropy. So now, if you take the evolution of the weighted relative entropy, so those very band terms will disappear. Okay, so in general, right, I will show you maybe at the end. So you see, we can treat a large family of interaction kernels, both in the stochastic case and or the vanishing viscosity case. So to be simple, right, you write K is the minus gradient of phi. I think we use V. So we can treat like V has a large smooth part, a small attractive part. Basically, this means attractive logarithmic case. As in the Peddler-Keller-Seeger system, and a large repulsive singular part. Like I showed you in last lecture, so what Sarfati and Durings can do for deterministic systems. Okay, right. So this is what I just discussed. So the problem of our previous relative entropy method is that we can treat essentially bounded solutions, bounded kernels, or in some negative subject space. But essentially, by integration by parts, they change everything to be some bounded things, bounded kernels. We don't need a lot of structures, but we cannot treat very singular kernels. So after that, so maybe not exactly after that. So modulated energy method is used in other places before, like is used by Sarfati in study of Gisborne-Landau, for instance. And so this method is very powerful. And so they can study mean field limit. They can show mean field limit for very singular, like Riesz type kernels, as we showed on Monday. So the crucial quantity there, right, their main object is the Coulomb norm or Riesz type norm, as I write on 2 days ago. It's something like this. It's mu n minus rho bar. So we mirror this with a norm. This norm depends on the potential V. You can define like this. It's basically, I put a 1/2 here so that we call this modulated energy. So then our real modulated free energy will have exact structure the free energy has like in statistical physics. Right, so the modulated energy is just the Coulomb or Riesz type of norm, right, as we said 2 days ago. Right, we compare mu n rho bar, right, and VA the potential function V. Right, so if everything is nice, right, there's no off diagonal terms, and you can just take Fourier transform, right, this term, this modulated potential energy or modulated interaction energy is just this. Integrate in the frequency space. Okay, so here mu n, of course, is an empirical measure. Okay, so this is a comparison comparison of the two previous methods. And so later, let's just fix the notation first. Right, this already said many times. It will be relatively straightforward. Okay, So we consider the stochastic systems. Now let's fix sigma is positive number. So here sigma is a positive number, and it's interacting first order system. So if everything is nice, let's say K is Lipschitz, or so we know the limit equation, the mean field dynamics is given by the aggregation diffusion equation, right? So this is the velocity field. This obviously coming from the Ito, the Laplacian term. If you have the noise here, right, you do the Ito formula, right? This is an extra term. It will come from there, come from the noise. Okay, so this is what people know, like in the coupling method, right? Okay, so in this lecture, we in particular focus on the case Vx is given by some attractive logarithmic potential, and we consider everything on torus for simplicity. Okay, so this equation, now the limit equation corresponds to the famous Peteler-Keller-Seigert system people use to model chemotaxis. So for this work, I talk about this in my lecture, in my talk, in PD seminar via Zoom, and Pierre-Emmanuel also talked about this in that PD seminar sequence. So you can find that on YouTube. Yeah, but this talk is more in detail. So because we already talked about the background. Okay, so let me just remind you, right? If everything is on R2, is on 2D space, the whole space. So if you take Vx to be lambda, right, to be this, so this is not the fundamental solution of Laplace equation, but it's because this is attractive, lambda is positive. So if you take a Laplace operator, right, you get 2 pi lambda. So right, so this parameter, right, so we kind of change the u or y to normalize, do the normalization. Okay, yeah, just to remind you, right, if you choose Vx equals this, we take a Laplace, you get 2 pi lambda Dirac and 0. Okay, yeah, this is just a rewrite of everything. And for Peteler-Keller-Seigert system, there are a lot of analysis work of this PDE. In last, I think, in last decades, there are a lot of study of this equation. It's a very, so for this system, right, there's a singular kernels, and they are competing mechanisms, two competing mechanisms. So this is the noise part. So this noise part try to diffuse the solution rho bar, right? They try to diffuse. And this part is attractive part, right? So as I said, this is attractive potential. So particles, they try to coming together. So this part is attraction part. This part is like diffusion part. So there are two competing mechanisms. For this PDE, there's a there's very famous work. So for instance, you can see the Blanchett, Dubino, and Bohdam in 2006. But there are many other works like after that or around that time. So the typical behavior, the key, the feature behavior of this PDE is they have a critical mass. So for 2D case, in 2 dimension, so they have a critical mass. So, but it's not like the system we used here exactly, right? So they kind of change everything. They change sigma to be, let's say, 1, and they use k exactly. So they use k, like for this case, they use k exactly as minus gradient v, and v is just the Poisson kernel. So it's this. Okay. So sigma you said to be 1. My memory might not be very precise, but it's like this. And now, right, so you just starting from a distribution, not necessarily probability distribution. So rho bar, 0 equals to m. So m is preserved. So the total mass is preserved, and m is a quantity, right? People use to identify the Wilcoxness or the blow up behavior of this system. So for 2D case, if m is less than 8 pi, like using those parameters, right? And if m is less than 8 pi, so this system is they have global in time solution. So, but if m is bigger than 8 pi, so then they have blow up. So in the end, every particles will just collide to form one huge particle. Okay. So we changed the notation a little bit, but it's essentially the same. But we just, because this is like temperature sigma, we want to put the temperature there. And so in the stochastic system, we put strength, noise or strength here, right? And we fix the mass to be 1, but we are changing the strength of the attraction. So we change the lambda. So we change the lambda here, and we fix the total mass to be 1, so everything, the initial data is a probability measure. Okay, so in our case, the classical work of Kato-Shiga system is the critical strength of the attraction is full sigma. So if lambda is bigger than full sigma, so the PDE system will have blow up behavior. So if lambda is less than full sigma, then we expect, then we will have global in time solution, right? If initially you have like nice solution. So the solution will exist in global in time, like for any t, you will have a regular solution. Okay, so we will be talking about mean field limit, right? So there are a lot of, not a lot, but there are several works like last 10 years on particle approximation to Petersburg-Kato-Shiga system. Let me just give you one example because this is a very good result. So the result basically said the following. So starting from the particle system, we consider the accumulation point of mu and t. So mu and t is a random stochastic measure, a random probability measure. So the accumulation point of mu n solve the Petersburg-Kato-Shiga system weakly. But this only works in very subcritical regime. So like in using our notation, lambda is less than full sigma, or using classical PDE notation, it's like the total mass is less than 2 pi. It's like 1/4 of the critical mass. Also, they don't have like a convergence rate, anything like that. So this based on like compactness argument. So you can select accumulation or a convergence subsequence, So we have the this convergence subsequence converges to a weak solution of Kato-Shiga system. So so our work will follow the previous framework I introduced like in last week. So let's just let me just remind you. Okay, so here Rouen. So here Rouen is joint solution, joint distribution of the particle system, and of course, right, the particle system is exactly the same we used before. The only different part is the kernel. So Rouen solves the Liouville equation coupled with initial data Rouen 0. Like for this work, you can even just think initially we choose the IID data, but right, you're probably already familiar with, right? Usually we choose like if you're using relative entropy, we will choose something like under this norm or on norm under this quantity, we have the relative entropy equal to 0, for instance. Right? Or these are very particular case. Again, right? We use a weak solution. We call the entropy solution to this Liouville equation. So in particular, right? So we need a weak solution which dissipates entropy because we need to control entropy. Okay. So in this setting, the main result is like the following, which I will show you the main step how to get this. Is like the following, right? We assume Rho(n) is the weak solution. Rho(n) is the entropy solution to the Liouville equation. And for simplicity, let's just assume initial IID data. And the potential is given by attractive logarithmic potential with the periodic correction VE here. So again, right, this is a weak strong type result. So we need the limit quantity, limit solution rho bar is really nice, and second order derivative, and the derivative are bounded. So this can be improved, but we made a strong assumption to get argument easier. Okay, and we assume the strength of attraction lambda, right, lambda appearing here, is less than 2D sigma. So for in particular, if we consider in 2D case, this is exactly cover all subcritical regime. In this regime, the PD will have global in time solution. So we do the analysis, and in the end, we will have the convergence of all marginals in L1 norm. And but now the convergence rate is 1 over n to theta. So theta is usually, and this now is not optimal. Theta is less than 1/2. Okay. In this lecture, we just want to show, to give you all the methods, right? All the main steps, the ideas to show this result. And okay, we will start. Okay, so the method we used is modulated free energy, as I said before. So now let's introduce this. Right, as I said before, we want to cancel variable terms like in 2D Peter-Keller-Segal case. So for this K, right, if you take divergence, since K is minus, so this is divergence. So now you get this, right? So this is not, so actually this is 2 pi lambda delta 0. There's a minus there, right? So here there's a minus. So it's a Dirac, right? So we must cancel this this term. Of course, right, to get this, there are a lot of computations, but I just tell you the final answer. It's very long computation. But this quantity the mimic the free energy people used in study of the Wilposians or Keller-Segal system. Yeah, I will give you more remark after I define this quantity. So the modulated free energy, we use this to compare two distribution, right? Rho(n) and Rho(n) bar. So Rho(n) is the joint distribution of all particles, right? So Rho(n) bar is just a rho bar tensor product n, right, as usual. Okay, so if we previous relative entropy, right, there's just a Rho(n) over Rho(n) bar here. There's no weights, right? There's no weights here. Okay, so now we introduce weights, right? Gn and G Rho(n) bar. So Gn is just a Gibbs mirror. It's like a Gibbs mirror. But very critical things is here, right? There's a sigma here. But if you just look at this, not very clear here. So, but the definition is very straightforward. I give you a configuration xn. So xn is just a point. just a point in just one configuration of n particles, right? Given this configuration, you can write the interaction energy of them, right? So then you put the you put 1 over sigma, right? This is sigma is like temperature, and you have like one quantity, right? This is called Gibbs. Usually this is called Gibbs measure. Okay, so this quantity are not usual, are not common. So what is this quantity? It's kind of, it's a tilted Gibbs. So why is tilted Gibbs? So this is a limit, right? So let's say we want to, this given x, what's that, right? If there's no, the last term, right? This is just a quantity, right? It's just a constant. If you ignore the time dependence, right? This is just a constant in time. This part, right? If you write something like this, we write something like this, is mimic the Gibbs measure, but with the limit distribution rho bar. But here it's not exactly that, right? So we write this way. So in the end, we can get quadratic terms. You will see that later. Okay, so G rho bar, right? The G rho bar is like this. And if you take the tensor product of this quantity, we get G rho n bar. So basically it depends on rho bar, and it also depends on the configuration x1 to xn. So it's just we plug xi here, we plug xi here. So you get G rho bar txi, right? You get this. You get this quantity, and we multiply them together, so we get a tilted Gibbs measure. So this is kind of tilted Gibbs measure, and we use this to weight it the previous rho n and rho n bar. Okay. Okay. So if we take everything, we add everything together, right? We simplify this formulation. So what do we get? Excuse me. Okay, what do we get? Okay, so we just simplify the En terms we define here. Right? So we have two terms, right? So one term is just the relative entropy, right, scaled by 1 over n, and the second term. So we call the second term Kn. So Kn, right? You expand everything. As I said before, right? So this is given by Gn, and this term is given by the tilted Gibbs. So right, if we write in this way, right? This is a quadratic terms, right? It's like you complete x minus y squared, right? So you get full terms, and it's something like that. So we can rewrite this, right? We can rewrite these terms, these three terms, actually it's four terms. If we write this full term together using empirical measure, so we can write this, right? This is integral, we integrate with rho n in the end. We get the following, the last term. Okay, so this term is just the previous modulated potential energy used by Sarfati and Durings. And what we call Kn here is just the expectation of the modulated potential energy under rho n. But in the end, we multiply 1 over sigma. So this is the inverse of the temperature. Okay. So we rewrite this, right? So the En is just Hn plus 1 over sigma. Then take the expectation of the modulated energy. So we rewrite a little bit, or we take 1 over sigma out. It's just a constant, because now we just consider the fixed sigma case. So now what the quantity En is, right? So if we ignore sigma, or if we just say sigma is 1, it's temperature. So the En term is it equals an energy part, right, which is Kn, right? Energy part is like interaction energy, and plus sigma is temperature, the temperature times entropy. So this exactly, this year has exactly the same structure as free energy in statistical physics. So if you know a little bit about the work, let's say in physics, Langevin dynamics, or the work by the GKO scheme, or some variational, yeah, some like Otto's calculus. This is very famous, like so, like maybe the energy becomes potential energy, but the entropy is still there, like times the temperature. And if you want to study the gradient flow of the free energy under with respect to the, let's say, Wasserstein metric, then you just get the Langevin dynamics. Okay, so EN has exactly the same structure as free energy in statistical physics. Okay, but in our point of view, so this quantity can cancel the divergence term. So here I just give you the final answer, but I skip all the computation details. So if we assume the potential is even, if you assume the potential is even, and rho dissipates entropy, and rho bar is the limit solution of the PD. So then you just compute the evolution of the previously defined modulated free energy. Okay, so then this is the inequality we get. Okay, so let me just make several remarks, right? So you can think the following way, right? If you take the time derivative, d over dt and en rho n bar t. So now you get several terms. So the first term is is kind of modulated Fisher information. This term has the sign, has a negative sign. So basically we didn't use any information from this term. So the difference of these two terms. And there's this term which appears in Safatti's commutation as well, right? I showed you, but maybe not exactly this form, but there's, let's say, phi x. Let's use x. So this is phi x, hx minus hy, and v is the potential, right? And this is quadratic terms, and then you integrate with rho n. Right, so this is the estimate, the crucial terms you need to estimate in the end. Okay. So, but we integrate, right? So here we integrate of on, we remove diagonal. So we put x not equals to y here. So this is just off diagonal. So hx minus hy. Okay. So if you just formally take the derivative, right? So you get several terms, and this term only help, but we don't know how to use the information of this term. You can call this modulated Fisher information, right? And what we really need to show is how to control this term. But we won't talk a lot in today's lecture. So why? Because so let's focus on like a easy part, right? So this part is not hard, but let's at least for Keller sake, for the Keller-Segal case, right, this part is easy. Why? For the Keller-Segal case, we know, so gradient V has singularity, but not very large, right? So it has the same singularity as in the Beer-Savart kernel. So singularity is like 1 over x. So if we use the regularity of the h function, so h function is just this. So this function, if we choose rho bar, the limit nice enough, regular enough, so h is Lipschitz. So we can use the Lipschitz property of h to cancel the singularity here. So we will get a term which is bounded. So this term is bounded. So we know how to control this term now, right? This is just this is exactly what we used the main estimate in our previous work, which maybe I just remind you a little bit. So the crucial terms we need to control is the following, right? So it's fxy. So f is bounded, but so let's say f L infinity is less than C0. So this C0 is order 1 quantity. And we can conclude, so this is a quadratic term. And we can bound this term by, let's say, 1 over 1 relative entropy, rho n bar. And there's also this term. Maybe let's put a C here, right? So this is exactly what the previous estimate, the main estimate we used. This is the type 1 large deviation estimate. That's what I called type 1, but it's not a standard notation. Okay, it's not a standard way to call that. Okay, so in the Keller-Segal case, to control En, right, control the right-hand side of the evolution of modulated energy is exactly the same as before. So now the critical part actually is to control from below of this quantity. As in Safathi's case, you need to show, right, as in her case, in modulated energy, as in her work of the Rees potential case, you need to show like this Kn. You need to show this Kn is almost or asymptotic positive. You need to show something like this, right? Maybe it's not positive, but as n goes to infinity, you need to show this is positive. Okay, so this is the same as in our case, right? And so we know a priori, right, if we just compare two probability measures by relative entropy, so this a priori is positive as long as it's well defined, right? As long as it's well defined, this is positive quantity. Then and we know how to use this to control things, right? We know this quantify total variation type convergence, like L1 convergence or marginals. So, but this is a new quantity, right? And this probably, right, is not positive, right? We need to show this really is a quantity which can quantify the convergence, let's say for marginals. Right? We can quantify, so this quantity can quantify convergence of the marginals, for instance, right? So this analysis for the Keller-Segal case is the most difficult part. How to get the modulated free energy effectively control the distance between rho n and rho n bar is the critical part, and listed for the Keller-Segal case. Why, right? So because the second case is trivial, as I just told you. But for more singular kernel, this is not. This is still a very difficult part, and we need to control quantity like this, right? This is what Safathi used as well. We need to control these terms by itself, right? By itself. So this is itself. but maybe it's not enough, right? We might need a correction term from relative entropy and also very small terms. You can see more detailed discussion in our short notes, like appeared in Laurent seminar, Laurent Schwartz seminar, the Schwartz seminar in France. Okay. Yeah, so in the following, let's focus on the part 2 first. And that's like how to establish asymptotic positive, asymptotic positivity of the modulated free energy or coercivity, right? So we do the following very easy computation first. And so the modulated free energy has two parts. So first, relative entropy. Second, interaction energy Kn or potential energy Kn. So we just want to control Kn from below. Okay, if we have this, right, if we have this, we are done. If we have this, we are done. And actually, this is true, right? So if we use some repulsive kernel, this is true already. So this is what Sarfati did, right, in her work. I presented in last lecture. So if you just choose repulsive kernel, like in Riesz or Coulomb kernels, then you can just bound Kn by a very small quantity, depends on n. So then you will have asymptotic positivity. But now, so we want to include some attractive kernels. As I said, in the Petelecki case, it's a very moderate attraction kernel. And so you must conclude these terms. So you will see where it comes from. But if we have this, right, we can control the Kn, the modulated interaction energy from below by like 1 over C. This is C is bigger than 1 by a small part of relative entropy and also a small terms. Then we can just we can just have the coercivity, right? So why, right? So if this quantity converges to 0, if this quantity converges to 0 as it goes to infinity, right? This goes to 0 as well, right? This is just a number, scalar, then this quantity converges to 0. Then we can use in classical serial Kuban Pin-square inequality to show the strong convergence of all marginals, right? That's exactly like what we did before. So then that's it, right? So the major goal here is to bound Kn from below by Hn or with possible small terms. Okay, so the key is the following, right? So this is just a remark. So in all our works, the key estimate looks like the following. We want to control terms like this. There's a function here, right? There's a function here, fxy, and this is just the difference of mu n empirical measure and the limit, and we take square, right? This kind of quadratic terms, and then in the end we integrate with we take the expectation with respect to joint distribution rho n. These are terms we need to control from above or from below. So these are large deviation type estimate. So there are two types. Like type 1 I showed in lecture 4, and type 2, if we have time, we can say more. It's a new type of estimate, which based on like how to use, right? How to use the red function and how to bridge the difference. I will show you a little bit of computation if we have time in the end. Okay. So this is the proposition, right? We get like which give you the lower bound of Kn, but it's not for all Kn. It's not for all Kn, but it's for some truncated Kn. Some truncated interaction energy. Okay, so the assumption is the following. So we assume, in particular, this assumption. So Vx is bounded from below by attractive logarithmic potential. This is attractive. And V is also in LP, and the gradient of V does not grow too fast. You don't need to know exactly the form of those assumptions. I will show you the basic ideas later. But very important thing here is we must cut this V to some very short range interactions. So if we did not cut this, so you cannot use the rate function, which vanish, to really control the Kn from below by relative entropy and small terms. Okay, so chi here, this is chi. So chi here is a cutoff, but this cutoff is cut off from all far field interactions. So give you a V, you cut off all far field part. Right? You just consider the near field interaction given by V. Okay, so the result is given by the following. Since we put a minus sign there, so we put a minus sign here. So so now the lower bound becomes upper bound, right? So if you ignore, if you put a minus, if you change minus to plus, right? So everything becomes bigger than minus delta, right? So everything is the same, right? So just write this upper bound is more easy to look. Is yeah. Okay, so let me tell you a little bit like how to estimate this term. How to estimate this term, right? So if we ignore this sign, minus sign, right? It's just the previous Kn, but there's one part difference, right? We cut. We only focus on the near field interactions. So if x minus y is bigger than 1, is bigger than eta, so we ignore that part. So that's the smooth part or far field part we should treat separately. So otherwise, here we cannot use the rate function, which some large duration rate function which equals to 0. So this is like technical part, but okay, you can ignore chi, right, if you want, but that's not true. Yeah. So let's show how to do this asymptotic positivity. Okay. Okay, let's rewrite this f beta, which is the functional. So this which is functional maps from probability space to real numbers. Okay. Again, right, we only focus on near interaction or near field interaction. Okay, so this is the inequality, Gibbs inequality we used many times. I just want to remind you. So is if you integrate, you want to change mirror. You want to change the mirror rho n to some nice mirror, let's say rho n bar, which is IID. So you compensate with relative entropy and also some rho n exponential terms. Right? This is a Gibbs inequality we use many times. So if we apply this to the previous truncated Kn, if we apply this to the previous truncated Kn, so what do we get? Okay, so let's use that. So this is f eta mu n, right? So so we choose alpha such that in the end we get delta, right? So we choose alpha equals to this. So we use the Gibbs inequality with alpha equals to 1 over 2 sigma delta. It's just this inequality, right? Just this. You can check this later, but this computation is true, is right. So we get a delta which is smaller 1, which is we need it, right? We need the this part to be less than 1, and this is extra term it comes from. Right? And this appears in many places in large deviation type estimate. Is some Rho(n), right? It's IID distribution, and you integrate exponential function, right, like this against this IID. But in the end, you take log, and there's 1 over n there, right? So like before, right? So like previous work, we need this is like this term essentially is bounded. This term is essentially bounded, but is uniformly bounded with respect to n. But you don't need that very strong assumptions. You only need this term does not grow as fast as like some e to n, for instance, right? So as long as this term does not grow very fast, you are fine. Okay. Okay. So so we want to control this term, and we want to show this term is small. This is crucial things we need to keep in mind. So everything is involving like how to control this and how to show this is small, right? So in the end, we can get a convergence. Okay. So it's not very easy to do that directly. So we pass to some regularized version of mu(n). So the idea is to let's introduce L epsilon. So L epsilon is a standard, like you can choose a standard modifier, and then right you let epsilon x to be like in dimension d, right? It's just this. Okay, so we passed mu(n) to regularized version, and this estimate you can check, but this is not that easy, but it can be done by a lot of like Holder type inequalities. So we can pass the exactly mu(n), the functional involving exactly mu(n), to the functional involve the regularized version of mu(n), right, which is L epsilon. But in the end, you need to pay with extra small terms. But those small terms is very small, right? You can choose epsilon depending on n. As n goes to infinity, this epsilon also vanish. So there are a lot of things playing with parameters. But anyway, so this is not this is doable. But we need lambda is strictly bigger than 1. If lambda goes to 1, the extra terms c lambda here, so this c lambda here will goes to 1, will blow up. Okay, so we passing from the exact functional involving the exact empirical measure to some regularized version, but we compare but it pairs with extra small terms, but those are fine. Okay, so let's go back one step, right? So later we need to control these terms, right? We need to control these terms. We need to show these terms is controlled by one term is like rate function and another smaller terms, right? So we can use some continual type, right, analysis to show the rate function goes to is 0, then there's only small terms remain. So in the end, right, you can show all those terms are small. Okay, so let's recall a little bit the notations, right, involving large deviations. So in general, right, we consider functional maps from probability space to real space, to real. Possibly it can be unbounded. So for this functional, we can define a rate function. It's called large deviation functional. It's just a rate function associated to this f. It's a number. It's a number. So you take these things. Right? You take these things. Take the maximum over all mu, and this gives you a number, and we call this IF. Okay. And the previous goal, right? If we want everything works, so we control these terms by a rate function like if eta plus some extra terms. So then the one goal, right, is to show this rate function or large deviation functional vanish. Okay. So of course, right, if, for instance, this case, f eta, right, if we recall f eta a little bit, right, if we recall this f eta a little bit, right, if we choose mu, right, to be rho bar, we choose, then, right, this term vanish, right, this of course vanish, right, because they're exactly the same. So if the first term vanish, right, if this vanish, and this is relative entropy, right, so if you choose mu to be rho bar, right, this of course is 0. So then you get if is 0, right? And so one way to show that is to show the rate function equals to 0 vanish is to show there's only one maximizer, and this maximizer is rho bar, right? So this is the later idea I will show and show you for certain case, right? So this type of functional f will have rate function of 0. Okay. So if you look at like Wardang's work, so this, so maybe more closely in the form is the work, as I mentioned, like Bernoulli and his collaborator. Yeah, I forgot, but you can look at lecture 4 for details. So this quantity, right, if you send n goes to infinity, it behaves like the rate function, the large deviation functional. Okay, so it's you can put in this way, right? This exponential growth, this expectation, this of the exponential grows exponentially, right? So this grows to like NIF, right? So if the rate functional vanish, right, then we can expect to give a uniform control of these terms, right? So otherwise it cannot be true, right? Otherwise it grows too fast. In order to show this term is small compared to n, right, vanish when n goes to infinity, you need this is 0, right? So otherwise it's not true. Right? Okay. Yeah. So this is the main estimate we will use. So let's just state this very fast. So in the we already mentioned this several times, right? This is what we will use. So this first is a rate function, like deviation rate function, and these are small terms, right? It involves a lot of quantities, but anyway, playing with parameter epsilon, this is small terms. Okay. When n goes to infinity, all these terms vanish. Okay. So in the following, one goal, right? So the major goal is to show the previous defined f eta has 0 large deviation function, right? This is one critical part. Okay. So, but let's assume everything is known. Let's assume this is known, and let's finish the proof first. Okay. Using the previous estimate, right? So we can change. Well, this is the term we need to control, right? And using the large deviation estimate, right? So we can using the rate function and extra terms, right? And now, right, the function f becomes this, right, the scaled version of f eta. And by definition, right, this is the supreme over all probability measure, and this is the rate function, the function itself, functional itself, and this is relative entropy. So the crucial step is to show this part equals 0, right? So if this is on non-zero things, everything is dead, right? So we need this 0. Okay. So this is just a remark on the choice of the parameters, because this so when we show this vanish, we need those parameter. Right? We need you will see that later. So let's skip this discussion. But okay. So to show this rate function, this logic derivation function of Vanish, is where we use Hardy-Littlewood Sobolev inequality. You people doing some work in Keller-Segal system are probably very familiar with this inequality. So this is where we use this place we use Hardy HLS. So it's logarithmic Hardy-Littlewood Sobolev inequality. Let's recall the notion a bit. Now this is a functional we use, right? This is a functional f, and we will write this a bit, right? There's a parameter here, and there's a cutoff, the near field cutoff. It's not a cutoff the singular part, it's cutoff the far field part, right? As I said before. Okay, and we assume this Vx has possibly has like attractive part, which is gamma log x. So here, excuse me a little bit. So gamma is like lambda before, but it's kind of, we change the notion. Here I follow the notion we used in our paper, but yeah, please forget everything lambda we used before, right? So this is just gamma. This gamma is like the strength of the logarithmic potential. Okay, so so if we choose Wx, right? If we choose if we put how to say that? So if we choose Wx, so I think here should be this right here. So if we choose Wx to be lambda minus lambda 2 sigma delta V, if we choose the x, right? So then we will have this estimate, right? We have this control, and we will use this in our assumption. We will use this in our assumption. By previous choice, lambda is slightly, let me see, is slightly bigger than 1, and delta is slightly smaller than 1. Gamma, so OR here is less than 2D sigma, and gamma is just in the subcritical regime corresponding to parallel Keller-Segal system. Okay, so under all those assumptions, like Wx is less than minus C log x, with C is less than D. And so then we have the following things. Okay, so let's say we define a rate a functional fw. So W is kind of quadratic type functional comparing mu and rho bar involving W, right? This is fw is exactly the Sarfati's modulated potential energy, right? Or interaction energy. Okay, so if we assume rho bar is really nice, and C is less than D, and L1 norm of this potential is smaller than delta. So delta is some critical number, which depends on, okay, so let me see. So delta is small enough, but so it's not like, it's just order 1 small, right? And if Wx, right, is have a pointwise estimate, it's not too attractive, then we will have the rate function or logic derivation function of Vanish. So then under this case, right, our previous choice of Vx like satisfies this condition, right? As long as you choose this eta small enough. As long as you choose eta small enough, then this W will satisfy the L1 norm will less than delta, right? So then you can apply this lemma to show right, this quantity equals to 0, and you go to you use the previous type 2 logic derivation estimate, you can get the lower bound for Kn, right? So then that's it. So now the goal is to show this lemma, right? And this is where we will use logarithmic Hartley Littlewood Sobolev inequality. Okay, so here is just a trivial remark. If you choose eta small enough, so then we can satisfy L1. We can satisfy this assumption. Okay. Okay. So let's give you a sketch of the proof. It's basically a complete proof, but I don't have time. I will skip a bit. Okay, so let's recall the logarithmic HLS a bit. You can find this in theory 1. It's a very old paper in 19th by Cullen and Loss. So this is a logarithmic interaction energy, right? The first, the left-hand side is some logarithmic potential energy or interaction energy, and you can control this by L log L, by the how to say that is entropy. You can control this by entropy and constant, which depend on the dimension. As long as this function f, right, is a probability density and it has the logarithmic moment, and the entropy is bounded, right? So everything and this makes sense, right? Now this is very useful, right? For people enlisted for study of the Pedelec-Keller-Seeger system, the PDE level, right? So it's a very famous inequality. Okay. So how we use this, right? We use this in the following way, like very easy way. We want to estimate this FW mu, right? This functional FW. So we just expand that, right? So this is FW, and then we minus this, right? So FW mu minus this, and we want to get the maximum one of this quantity, right? We want to find the maximizer. Okay, so so we expand the quadratic terms here, right? So we get these 3 terms, and by using logarithmic HLS, it can be controlled by 2 terms, right? It's C over the entropy, right? So we over rho bar here, and we added bank here, right? So it's minus here, we added bank, and so we just copy here, and there's a minus here, right? So this is the term, right? Is these 2 term collapse, and here we just using the trivial bound, assuming rho bar is nice and W is L1. That's this is the X terms coming from here. Okay, so we have the upper control of the functional we want to maximize. Okay, so this is upper control. This is upper control, right? So we rewrite it here. Okay, this term is positive. This term is positive. So let's assume if we have a maximizing sequence. Okay, excuse me. So since this is positive, right? This is always positive as long as it's defined, right? So this you can ignore this term, and this W, this rho bar is all fixed, right? So a priori, this functional we want to maximize is bounded from above, right? So we can choose a maximizing sequence mu(n), right? Of course, this quantity is bounded from below, and is also bounded from above by this quantity. Okay, so we can show, right? So we can show this is bounded in L log L. So otherwise, this will be like this is not bounded in L log L. So this will be very large, and this will will converge to like minus infinity. Right? It's not possible. So mu n, right, maximizing sequence is bounded in L log L, and any weak limit is a maximizer, is a maximum. Is a maximum. Okay, so let's choose one maximizer, mu bar, and we want to show this mu bar actually is unique and which agree with rho bar. So by operational approach, right, standard approach, you can check this rho bar satisfies this inequality, this equality. So where kappa is constant such that mu bar is a probability density. So then the following just computation is so we choose mu bar, right? We choose mu bar. We can solve this, right? We can solve this. Just write this in a mu y. You can check, right? If you choose mu bar like this, you can solve that exactly. It's just another way to write this equation. Okay, so if we do this, so okay, so the following is just like stability estimate. It's not very hard, but okay. So we introduce a new notion U, right? U is like given by W convolves mu bar minus rho bar. So you can write U is a solution to the following equation, right? Just write mu bar according to U, right? So anyway, and so in now, right, all the goal is reduced to show for this equation is a nonlinear elliptic equation, only has one solution, U equals to 0. As long as delta is less than 1. So if you show this, so you get mu bar is rho bar, which is unique maximizer, and for this maximizer, the rate functional is 0. The rate of the large deviation functional is 0. How to do this, right? So we make the following observation, and so and then right here, so U is minus W convolves mu bar minus rho bar. So using the Gibbs inequality again, we can show this U is actually bounded. So why, right? So U is actually, right, is the difference of two convolution. So for the convolution with respect to rho bar, right, so this is bounded, of course. We want to control this part. We want to get control of infinity norm. So this actually can be easily seen by Gibbs again, which is bounded, right? And so here we in particular need to use C is less than D. C is less than D. Okay, so now the U is bounded, and we can estimate E to U, right? So we can show MU is bounded from above and bounded from below. So now we can give the L1 estimate of mu bar and rho bar. So it's all trivial computation, all straightforward computation, and you can do that. In the end, we use this, and we can estimate L1 norm of U, which is controlled by L1 norm of U. And if you choose delta small enough, let's say less than 1 over C, C is the universal constant, which depends on rho bar in particular. So in this case, we can show we only have one unique solution, U. Okay, so this is why the previous estimate, we need the near field cutoff. If you didn't choose the near field cutoff, at least you don't know how to show the uniqueness very easily. Okay. So for the smooth part, right? So, previously we choose a near field cut, and we show for this near field cut, Kn, the interaction energy, the modulated interaction energy, has rate function 0. But how to control the large smooth part, right? We can also include the large smooth part, right? We already cut them. We need to consider this large part. So how to do that? So I kind of abuse notation. So we call the far field part of V is W again. So we define the far field modulated energy as KNW. So this is KNW, and the form is exactly the same, right? So the only thing change is we change V to W, right? We change V to W, right? Here all become W, right? Okay. So we know, so we previously, right, we know how to control the total. This is total Kn, right? We remove the far field part, right? So this is a near field part. We know how to control this from below, right? As before. So now we need to estimate this, right? The far field part, right? So we just do the computation. We want to compute the evolution of the KNW. So which is exactly like these terms, right? You don't need to know the exact time evolution of this, but since W is very nice, it's far field part, there's no singularity, it's W to infinity. You take second order derivative, it's also bounded. So this term is bounded, right? This term is bounded, this term is, okay, so this is V. I should double check. But anyway, so this is bounded because it's evolution against Roba. Yeah, maybe please double check this. Yeah, there is, it should be V. Okay. So anyway, so this term is bounded, and this term is bounded. So we can using our type 1 large deviation estimate again. So we can show, right, this, right, you can put the plus here, or you can remove this plus. So either minus or plus is all works, but here we really need minus sign. So right, so here it doesn't depend on the sign here, right? So if you know, if you see our previous like division estimate, it doesn't really depend on the sign. Okay, so the time evolution of this can be controlled by C, can be controlled by relative entropy and 1 over n. Right, so this actually is critical. This is actually optimal. Right. Okay, so we can combine everything together before and give you the proof of main theory. So let's just combine everything together. Okay, so yeah, I might be over time, but okay, so let's combine everything together. So the time evolution, right, is the first is given by, right, those two terms. As I showed you, so this term can be controlled by relative entropy and 1 over n, right, up to a constant, right? So the previously minus the far field part is also controlled by this. So we can estimate the difference, right, is also controlled by this. Previously, right, we know, right, the near field cut, right, the near field part of the Kn is bounded from below, right? Previously there's a minus, so this is upper bound, right? But now it becomes plus, so it's lower bound. So we know, so how to, okay, so this is what we get. So excuse me. So, okay, yeah, so that's right, right? We remove this part, there's just a relative entropy plus the near field part. So it's bounded from below by this, right? So there's a relative entropy 1 minus this, right? So we just get that. So if we rewrite this a little bit, right? So Hn can be controlled above by this term and an extra term, right? So we can using the Grunwald, right? So we can using this term, right? We can previously this is just a relative entropy, but now we can change a bit, right? we can change the relative entropy to C2 this quantity plus this term. And previously they are C2n, but C2n is observed here. Okay, so using Grunwald, we can give the control of this quantity. Okay, so then what we get. Possibly you need to put absolute value here, but this, yeah, please check the details. And use the far field part is controlled by relative entropy plus 1 over n. So we can get, we can change the initial things by this, right? We just change the initial to be this, right? In this part to be this. So then finally, using the coercivity or almost as in positivity again, right? There's a C here, and this is this part plus C over n sigma, right? So you put everything together, right? You get this. So if we assume initially this quantity goes to 0, right? This goes to 0, right? Previously we have chaotic condition, right? So this is 0, this is 0. Even this is not 0, right? It's small. So as n goes to infinity, right? This goes to 0 for fixed time t. So we have convergence of relative entropy again. So we have convergence of n in k marginal as before. Okay. So this is the wrap up of our previous argument. There's one part I want to mention. It's called large deviation estimate. I call it a type 2 in our work, but it's not a standard notation. So how to do this? So this is a combinatorics argument. The idea is the following. So we decompose the order, the cube, right? Let's just call it the cube. Maybe here is just a square, right? You can think this d-dimensional cube, and we divide this, right, to be many sub cubes. So each one, right? So here this is m, and there are m to d copies, right? We divide the cube or torus to md disjoint hypercubes, right? Each of them has size 1 over m, and we can define approximation LM of Dirac. So this is the very particular definition. So this is really so this is not like the previous like Euro modifier, right, or approximation of Dirac. So this way is very easy to do combinatorics. Okay, and you can see, right, so this is a kind of convolution of F. Okay, and you can check, right, this LM is approximation of Dirac, right? Because if you choose F is Lipschitz, and F, and if you compare Fx and the convolution of F against LM, so this converges to 0 as M goes to infinity. Okay, so what we really need to do is the following, but there are other bridge, like how to pass LM, this very specific modifier to the regular modifier, right? How to pass from mu n to L epsilon, a regular modifier convolves mu n, as before we used to this estimate, right? There are also other steps, but this is crucial combinatorics argument, right? We need here. So yeah. So this is okay, like e to n, but instead of previous scenes, right? Previous like the quadratic terms here. So now it's just right, just the L log L, right? The relative entropy type terms here, and we can show this is small, right? This is small in the sense of you take log first and you divide by n. So as long as MD is relatively small, right? So then this since 1 over n log of this quantity is small. Okay, So this is the estimate we needed, right, to complete the type 2 light deviation estimate we used before. It's a crucial term. One critical commutation is the following, right? So this is a term we need to control, right? Like before, right? It's L epsilon convolves mu n. Mu n is empirical measure, and we need to show, right? This is small. This term is small. We need to show this is small, right? How to do that? We plug, right? So this is a functional, and IF is the maximal of certain things, right? Of IF is the supreme over all mu, right? So it's F mu minus mu log mu rho bar, right? So then, right, for typical choice, for any choice of mu, right, so this is bigger than that, right? So F mu, right, for typical choice of that is less than IF plus this mu log mu rho bar. Okay. So here we just, right, so we just, so here mu is L epsilon convolves mu n, right? So this part can be put away, right, which give you this term. And the remaining term is just this, right, just this. And we need to do this exactly. But you see, right, it's different, right? So here L epsilon is the standard modifier, right? It's a usual modifier we use. But previous combinatoric arguments is use a very particular LM. This is different compared to L epsilon. So there's a difference between them, right? You need to control as well. Okay, but anyway, in the end, we can do we can do that. Okay, so this is the idea. Maybe let me spend 10 minutes on the last few parts. Okay, so in general, we can combine all those ideas to treat the general kernels. Here is just an example. You can see our notes and upcoming papers for details. So so in general, we can treat the following kernels. So for the stochastic case, right, sigma n all equals to sigma, which is positive, the stochastic distance. So sigma you can see is a temperature. So in this case, we can treat attractive part, but this attractive part is not too singular. It's a moderate attractive part, which is logarithmic, right? So is this, right? It's this. But for repulsive part, it can be large, right? It can be like Riesz or Coulomb or any other like that. For the vanishing viscosity case, right, which is very important in random matrices theory, so in this case, we cannot treat attractive case, but we can treat general repulsive potentials. And so you can think in the following way. So as sigma n goes to 0, so our modulated energy, so you must multiply sigma n there. So then this is the right scale. So actually, right, so I think, right, so that's what we did later. So En is Hn plus 1 over sigma Kn. So let's put tilde here, right? So this sigma n, right? But we should really consider this one, right? We should really consider this quantity. So this is sigma n Hn plus Kn tilde. So when sigma n goes to 0 case, everything, so sigma n vanish. So all the concentration, all the free energy concentrate on the potential part of the interaction part, Kn tilde. So in the end, we use Kn tilde to control the convergence, of the marginals. Okay, so it's not like for the vanishing viscosity case, we did not use the strong, we cannot get the strong convergence, right? We can only get weak convergence via like Weierstrass distance, for instance. Okay. In particular, right, as this assumption, we can cover Riesz potentials with possible like perturbations. Okay. Okay, so there are many possible questions can be considered. Let's just mention a few. So a major open problem, like for instance, for people, analysts for people doing kinetic theory or PDEs, so there's a very significant case is still remain, is still open now. So as I mentioned in Monday, so Sarfati and Durings, they did the monokinetic case of Vlasov person, which is Euler person in pressureless form. So, but the full case, like F, right? So the phase space density is there's a smooth, like how to approximate this, how to show the mean field limit from classical Newton dynamics to the Vlasov person system is still open. Is still okay. And there are also many questions remaining in our problems, like how to better use the modulated Fisher information, like Hamiltonian system, like in general, how to polish those methods to say something more, right? There's many questions. I don't want just to read the slides. I didn't use these exact slides. Yeah. Okay, so there are general this type large n type problems. So recently, there are many people interested in this direction. Like at least there are several groups working on quantum many particle system. There are more people working on quantum many particle system. Like in particular, like deriving nonlinear Schrodinger equation, like Hartree equation, from n particle Liouville equation, like from master equations. There are also several, maybe two major groups, like deriving Boltzmann type equation, collision type equation. For instance, like the classical Landau type, not Landau, classical Lanford work, Lanford result, like how to derive the from collision model to Boltzmann type equation, type kinetic equations from microscopic model, like from collision models. This is the original work by Boltzmann. Right? There are many this type of works, which recently is very popular. Except like theoretical side work in this direction or in this favor. Recently, I collaborated in particular with Zebang Shen on algorithms like emotion learning tasks based on interaction particle systems. So you can, at least I give the two papers we submitted recently. So one is like particle-based, particle-based algorithm. So we use n particles to search the sinkhole barycenter. I mentioned maybe in lecture 3 in more details. And the second one is like we use generative models. So we want to search, we want to find the parameters. We will use those parameters to represent distribution, and we tutoring these parameters to get a better representation of the distribution. So the actual work, right, is like we use natural gradient based on sinkhole divergence to update these parameters. The practical result is very good. Yeah. So I didn't want to talk too much about that. There are also many other theoretical works related to these mean field limit problems. I list several. I don't want to discuss in full details. If you're interested, you can let me know. Yeah. I think I will just stop here. Yeah, and these are the reference related. These are all my papers related to these talks, this series of lectures. And thank you. And if you have questions, I can answer. Otherwise, that's all.